Hi everybody, this is the last class on combinational circuit design and analysis. As you know, we've covered a wide spectrum of different combinational circuits so far. That includes but not limited to XS3 code conversion, encoders, decoders, multiplexers, to name a few. And now we are left with one major type of combinational circuits called arithmetic functions. In today's class, we'll cover a bunch of basic arithmetic functions, including binary addition and multiplication. Such digital circuits lay the foundation of arithmetic logic units found in modern CPUs and many other electronic devices in the market. For example, a generic arithmetic logic, also known as ALU, unit is capable of performing two important functionalities. One of them is execution of logic operations such as AND, OR, and inversion. Another important functionality is execution of arithmetic operations such as addition and subtraction. Today's topic is a bit wider than the material that will be covered here. However, we will be touching upon those more trendy, stylish topics moving forward. To make the message crystal clear and succinct, let's just jump right to the point where exactly the arithmetic starts and reveals the treasures of the digital binary world. Binary addition. It is an operation that lays the foundation of most of the major arithmetic operations in binary world. Half adder, whose name and rationale behind it would be clear later, is the most basic binary adder, which takes two inputs as input and provides 2-bit output. The inputs are A and B, having logical values 0 and 1, and the output S is the sum of the 2 bits modulo binary 2. In other words, as long as we do not have any overflow, the sum will be the binary sum of 2 bits. In case we have an overflow, that's the last row in the truth table, you can see in that slide, that is to say A and B both equals 1. In that case, an auxiliary variable is needed to overcome the difficulty. That new variable is called the carry, also represented by the literal C. The carry happens only if both A and B are 1. It's also when the overflow happens. Remembering that all different 16 functions exist for 2 input gate combinations, we can realize that the C output is exactly the same as the truth table given for AND operator. And S output can be implemented using XOR logic. And half adder, therefore, can be implemented using an XOR gate and an AND gate. There are also alternative ways of implementation. Here I show the Boolean expressions for S in both SOP and POS form. The corresponding expressions for C suggests that C can be used as the common term and thus S can be computed based on C, as shown by the second alternative expression. A class exercise asks about the number of NAND gates to implement the half adder. So think about the minimum number of NAND gates in your half adder implementation. Notice that half adder is a nice tool for performing the binary addition operation, but there is something missing with it. Think about adding 2 sequences of binary bits. In that case, there are multiple stages of binary bit additions. It might be the case that the previous binary addition shall create a carry that propagates to the current addition stage. In that case, the half adder cannot account for that. The full adder, on the other hand, is like the completed half adder with the addition of a carry bit from the lower stages. Therefore, it has 3 inputs, A, B, and C in. And like the half adder, it has 2 outputs, S and C out. This way, the generate carry can be propagated to the next stage. If we draw the kernel maps for each output, S and C, we can realize that the Boolean expression for them are as given by S equals A B prime C n prime plus A prime B C n prime plus A prime B prime C n plus A B C n. And likewise, C out, that's the second output, is given by AB plus ECN plus BCN. The corresponding truth table is also shown to the left of the slide. As always, next thing we do is to identify the common terms if there is any, as we have seen in our combinational circuit design class. Previous lectures have a lot of examples explaining that. Let us use parentheses to group terms for S and recognize that the terms inside the parentheses can be implemented by either using XOR or XNOR gates. From a bit top level, the final result is the XOR of A, B, and C, and that gives the sum output, S in this case. Using a similar strategy, we can also identify A XOR B term that exists in the modified Boolean expression for C out. Please follow the steps to convince yourself. This common term is labeled as carry propagate. The AB term, A and B, is named as carry generate. The significance of these terms will be clear later in the course. The full adder's logic diagram is as shown. Based on our previous arguments and Boolean expression manipulations, all we need to use 2 XOR gates, 2 AND gates, and 1 output OR gate. This sort of implementation leads us to use 2 half adders to make 1 full adder as shown at the bottom of this slide. You can label the inputs and outputs of half adder to see that. The output OR gate is still used to complete and completely compute the carry out. Yet each XOR combined with 1 AND gate makes a half adder, and hence they are both replaced with a half adder logic box as shown. It might be useful to implement the full adder using half adders when we run out of all full adder ICs at hand. Half and full adders can be used to add binary numbers. A straightforward way to implement a 4-bit adder that adds 2 binary numbers is the cascade 4 full adders as shown. The bits are added with full adders starting from the least significant bit position to form the sum and the carry bit. The input carry C0 in the least significant position is 0. The next carry bit is the output carry of the previous full adder. The output value is transferred into the input carry of the next full adder that adds the bits 1 higher significant position to the left. The sum bits are generated starting from the rightmost position and are available as soon as the corresponding previous carry bit is available. So all the carries must be generated to be able to see the correct sum bits appear at the outputs S0, S1, S2, and S3. Please also observe that if we were to design the circuit using a conventional way, it would require a truth table with 512 entries, since there are 9 inputs to the circuit. Therefore, an iterative cascade of a set of standard functions leads to a straightforward implementation. A cascade of AND full adders leads us to implement an N-bit ripple adder. However, the problem with the ripple adder is the carry propagation delay. It's the length of time for the ripple carry to propagate the carry bits from the least significant bit position to most significant bit position. In our example of 4-bit ripple adder, each internal half adders cause a gate delay, making 2 gate level delay per full adder. For a 4-bit ripple adder, a total of 8 gate level delays are incurred. Carry propagation time is an important feature of the adder because it practically limits the speed with which 2 binary numbers are added, and we may be after faster implementations at the expense of higher implementation costs, such as more expensive circuit components or more silicon area consumed, in other words, more complex circuitry. One obvious solution is therefore to employ faster gates, which is usually very expensive. Another alternative solution is to slightly increase the complexity of the circuit to allow more parallel additions to minimize the propagation delay. The most widely used technique is the carry look-ahead logic, which we will discuss next. Carry look-ahead generator is invented to remedy the propagation delay as a top priority objective. This adder can be derived by first identifying 2 important carry variables that are named as carry propagate, denoted as PI, and the output of the first XOR operations, and carry generate, named as GI, and it is the output of the first AND operation. Both has single gate delay. Based on these 2 nib variables, the output sum and carry can be expressed as in terms of these. Using substitution, we can rewrite the carry out for each bit position, namely C0, C1, C2, C3, and C4. This substitution rule gives us a bit more complicated expression for these variables. These carry out variables can be written, therefore, in terms of P0, P1, P2, P3, and G0, G1, G2, G3. This means to compute C4, we no longer need to wait for C0, C1, C2, or C3 because we directly computed its value by substituting previous carry values. This means that we do the same computations more than once, and that adds additional logic to our design. Therefore, at the expense of more hardware and complexity, we gain timing advantage. That is, we do not need to wait for all carries to be computed and minimize the gate delay between the input and the output. So after establishing the relationship between the carry bits and the carry propagate and carry generate variables, PIs and GIs, we can draw the logic diagram of the carry look-ahead generator circuit as shown. By the way, I've drawn this logic diagram using the software Logisim. You can realize that there are 9 inputs and 4 outputs where 4 carry bits have the same propagation delay. Next, we use this combinational circuit to implement the 4-bit carry look-ahead adder. So finally, we obtain the shown combinational circuit that has 9 inputs and 5 outputs, that adds 2 4-bit numbers and generates 1 4-bit output with a carry bit. As noted before, the special thing about this circuit is the way we design the adder, such that the carry propagation delay is minimized. This means faster computation as well as faster response to the given request. This is achieved at the expense of more gates and complexity. So after reviewing the addition operation, let us look at if we can use the same circuit to implement a subtraction operation. To be able to understand and design the subtractor circuit, we need to review our background about unsigned and signed binary numbers and the binary subtraction operation that was the subject of our previous lectures. For the unsigned binary numbers a and b, remember that a minus b can be implemented by adding a to 2's complement of b if a is greater than b. It is usually easy to compute the 1's complement first, and then 2's complement can be obtained by adding logical 1 to the least significant bit position of 1's complement. This can easily be realized by setting C in our previous logic diagram, if you remember. If b is greater than a, the result is the 2's complement of b minus a. In other words, the negative a minus b. For signed numbers, remember that the most significant bit is the sign bit, and the same rule applies. The output will be equal to a minus b only if there is no something called overflow. In other words, or in other cases, underflow. This means that the output range of values should be representable given the number of bits used. Overflow can happen in unsigned numbers as well. However, it's a bit harder to detect for signed numbers. Next, we explore more about this phenomenon for both signed and unsigned numbers. For n-bit unsigned numbers, let us say if the final carry out bit is non-zero, then we locate an overflow problem in our system because the arithmetic operation produces n plus 1 bits to represent the output, which is not possible in the hardware. If you had a piece of paper to perform the arithmetic, you wouldn't have this problem, however. But in hardware, you've got only limited number of bits to represent a number, which is n in our case. For signed numbers, on the other hand, an overflow can happen only if both numbers are either positive or negative, because addition of a positive and a negative number is guaranteed to result in a number within the permissible range. If we carefully consider the overflow detection for signed numbers, we can observe that the overflow will happen if the carry into the signed bit position and the carry out of the signed bit position are not equal. To see this, let us give 4-bit adder subtractor circuit example and walk through the logic that detects the overflow. Then the general case will be easier to understand. If both positive, for overflow C3 must be 1. And since A3 and B3 are zeros, unsigned, the carry C4 is 0. Thus, V, which is another variable that helps detect the overflow, is 1, meaning that there is an overflow. If both negative, to generate an overflow C3 must be 0 due to negative numbers represented in 2's complement form. Then since signed bits are 1 in signed logic arithmetic, the output carry C4 shall be 1 and hence V is 1, meaning that there is an overflow detected. Therefore, to be able to detect if C3 and C4 are different, we apply an exclusive OR logic operation to these outputs to generate V shown in the figure. If V is 1, then the 4-bit result of the number fit in the place provided by the 5th bit position, and it's the actual sign bit that is shifted out of the position. This slide is basically showing us that the same hardware circuit can be used to implement both binary addition and subtraction at the same time. It is, of course, left as an exercise to draw the same adder and subtractor circuit using the carry look-ahead logic. It should be possible. The control input you can see on the right top of this slide, M, is used to select the addition or the subtraction operation by setting M equal to 0 or 1. So after reviewing addition and subtraction operations in binary domain, let's talk about decimal adder. Most calculators and special computer softwares does addition operation for decimal numbers and display the output in decimal number system. However, all the computations are performed in binary domain. To be able to carry out additions using the decimal number system, we need decimal adders, which add 2 decimal numbers and present the output in decimal format with a possible carry information. Implementation of a decimal adder is pretty straightforward using binary adders, however. The design needs to determine first the mapping between the binary representations and the decimal numbers, expressed in other words, the coding we use to represent decimal numbers using bits. Right now, I will assume a well-known coding scheme, binary coded decimal, also known as BCD codes. I think we've covered that in one of our previous lectures. I want you to go back and review those. I want to bring something to your attention now. When you sum two decimal numbers, the maximum number you can get is 18. And plus 1, perhaps due to a carry from the previous stage, gives you 19. When you compare the binary sum representation and BCD representation, you can realize that these two representations differ for decimal numbers starting from 10 to 19. The rest of them are the same. So more explicitly, I've drawn a table. This table shows the binary sequences that differ for the binary sum and BCD sum. The decimal number representation from 0 to 9 are common to both sums because it is a single decimal digit and their representations are exactly identical. No conversion is needed for them. When the sum occupies two decimal digits, for example, when 5 plus 6 gives you 11, the binary representation of 11 and its BCD representations are different. Notice that we have the maximum possible value being 19, which is obtained by 9 plus 1, where the extra 1 could be a potential carry coming from the previous addition stage. The problem is to find a rule by which the binary sum can be converted to correct BCD digit representation of the number in the BCD sum. As we have seen in one of our homework questions, the addition of decimal number 6, the binary 0110 to binary sum, will convert it to the correct BCD representation and produces the necessary output carry as required. So the next question is then, when do we need to add 6 to the sum for conversion? Apparently we don't need them all the time. If we close the inspect the about truth table, which by the way lists all the possible cases that requires conversion, we can see that when k equals 1, we need conversion. That's the first noticeable difference. In addition, k being equal to 1, the rest of the numbers have a 1 in E8 position. However, 1000 and 1001 has 1 in the same binary position, and they don't require conversion. To differentiate that, we also require either E4 and E2 to be 1. Therefore, the condition for conversion is given by k plus E8 in parentheses E4 plus E2. In this case, if c is 1, it is necessary to add the decimal 6 or binary 0110 to the binary sum and provide an output carry for the next stage of addition. A logistic implementation is shown for you and for convenience using 8 full adders. As you can see, 0110 binary number is added in the second 4-bit binary adder implementation, and the extra logic is to decide if decimal 6 addition is necessary. You can also use 7-segment displays for debugging purposes. When you experiment the BCD Adder in Logism software, I highly recommend that for you. The BCD Adder is implemented using full adders. If the application is delay sensitive, we may replace the cascade of full adders with a binary adder that's based on carry look ahead logic. It is left as an exercise to implement the same circuit using carry look ahead logic. Next, it's time to explore the binary multiplication logic. The rules for making two binary numbers multiply is quite similar to the rules of decimal number multiplication. Single-bit binary multiplication is an AND operation because the output of the multiplication operation is 1 if and only if both of the inputs are 1, which defines the functional operation of an AND gate. So let us walk through an example that's shown at the bottom of this slide, where the multiplicand A is of 4 bits and the multiplier B is of 2 bits. We also index the letters to indicate the bit position for each binary number. When we exploit the ordinary multiplication rules for binary numbers, we have the following result. So the output consists of 6 bits given by the corresponding expressions in this example. I've named the output bits S5, S4, S3, S2, S1, S0 in decreasing significance from left to right. The left most significant bit position is apparently the final carry bit, and S4, S3, S2, S1, S0 has a Boolean expression, corresponding Boolean expression in terms of A and B. If we attempt to implement the multiplier using a combinational circuit, the straightforward topology of logic gates and modules looks as follows in this slide. We can realize it using a 4-bit binary adder as shown. AND gates are used to carry out the multiplication. As you can see from this figure, 4-bit binary adder is a building block of a 4-bit binary multiplier. As a 0 bit in the first 4-bit input to the binary adder is needed because of the inherent shift of the multiplication operation. Recognizing such a shift in multiplication rings the bell for alternative implementation techniques for multiplications. For example, one potentially less area-consuming implementation would be based on sequential logic, where the shift operation can be handled by flip-flops. Such circuits will be covered later in the class when we analyze and design sequential circuits. Let us finally think about an exercise, as we have given examples of the general case that if we had x multiplier bits and y multiplicand bits, how many AND gates and binary adders we need? Answer to this question will also help understand why we need better alternatives for multiplication of long binary sequences. Finally, I'd like to give you a brief about binary comparators, or also known as digital sequence comparators, which constitute a piece of hardware that admits two binary sequences and ascertain whether one of the inputs is greater, less than, or equal to the other input. The most straightforward way of implementing binary comparators is to use conventional AND, OR, and NOT gates, A, O, I gates in other words, which is usually what textbooks do, and you can find a rich inventory of such implementations in literature. Since as of now we are familiar with fancy combinational circuits, we will present an implementation based on decoders. Before that, though, we need to put some thought on the logic needed to realize the comparison task. So next slide, we'll examine this logic. So let us consider two binary numbers of n bit long. A is given by A sub n minus 1, A sub n minus 2, blah, blah, blah. And B is given by Bn minus 1, and Bn minus 2, dot, dot, dot. There are three possible outcomes out of a comparison job. 1, A equals B. 2, A is greater than B. And 3, A is less than B. In the equality case, we should have all the inputs equal to each other. For A greater than B, we check the most significant bit first. If AN is greater than BN, then we need no more comparisons, and we can simply conclude A is greater than B. In case of most significant bits being equal, we check the next bit, and so on and so forth. This is given by the second row. This logic can be expressed as AN being greater than BN, or AN equals BN, and EN minus 1 greater than BN minus 1, etc. Similarly, A is less than B case can be implemented by checking the most significant bit, and in case of quality, we move on to check the next bit, and so on and so forth. When we examine the output of a decoder, we basically figure that if one of the outputs AB and A prime B prime is logical 1, then we can assert that bits are equal. If AB prime is 1, that means A is greater than B, because this output is equal to 1 only if A is 1 and B is 0. Similarly, if A prime B is 1, that means A is less than 1, because this output is equal to 1 only if A is 0 and B is 1. Therefore, a decoder is capable of producing all three cases using an extra OR gate as shown. The logic that consists of a decoder and an OR gate oriented as shown constitutes the building block of a binary comparison logic circuit in our example. So when we use the building block for implementing a 3-bit comparator, we obtain the logic circuit as shown in this slide. You can simply observe that we need 5 more AND gates and 2 more OR gates to implement the whole logic. Let us walk through it, starting with the equality case. Here, what you see is the case implementing using an AND gate, that all bits are equal, and they have to be equal at the same time. The connection for this case is shown with the red wires. Next, we examine the case when A is greater than B. For this case to be true, we need A2 greater than B2, or A2 equals B2, and A1 greater than B1, or all of the bits are equal except A0 is greater than B0. This logic is implemented 2 AND gates and a final OR gate. The connections, again, are shown in red wires. Finally, similar logic can be implemented for the case A is less than B, following the steps of the previous slide. Again, the connections for this case are shown using red wires for a better tractability. Make sure that you follow the steps needed to construct the correct logic for any binary sequence. It's left as an exercise to find the number of extra and or gates to implement an 8-bit binary comparator. Can you implement an 8-bit comparator using 2-bit comparators? Is another interesting question. Anyways, think about all these questions. Let me leave you busy and thinking about these questions, and I finish today's class with final remarks. In summary, in this class, we covered the most fundamental arithmetic operations related to combinational circuit design. We have shown how to use our background information to deal with combinational circuit design framework, particularly when it comes to execute arithmetic operations, which, by the way, lays the foundation of CPU and controller design. After establishing a solid understanding of combinational circuits and touching on a few important logic circuits, which belongs to that class, in the next lecture, we will have a dive into sequential logic and circuits with memory. None of the circuits we covered so far had this unique feature, that is the incoming information bits that are stored to set the state as well as used to affect the future outputs by way of maintaining individual memory. We will see sequential logic is the building block of our motor storage devices. A lot of excitement and adventure are waiting for us, so stay tuned. Needless to say, please feel free to drop any questions you may have about today's lecture into my email box, and I will be more than happy to help you with your questions. Thank you very much.